first speaker this afternoon is Claude Mareau from Genève University of Science and Technology from Lyon, France. I ask him to apologize for my French. He's going to speak on effects of 2,6-diethylaniline and H2S on HDN of chlorine. Dr. Mareau. You want to use mine?
So to start this afternoon session, I will talk on the effect of 2,6-diethylaniline and hydrogen sulfide on the mechanism of denitrogenation of quinoline over conventional sulfided nickel molybdenum supported on gamma alumina catalyst. So this work was performed at the School of Chemistry of Montpellier in France and in the framework of a European contract between GERT and CNRS on new catalysts for HDN on heavy cuts. So it's well known that the effect of hydrogen sulfide or its precursors on the mechanism of HDN of quinoline, so H2S increased in a significant manner the rate of HDN of quinoline, as it was shown by Satterfield some years ago. In a similar way, water or precursors also increase the rate of HDN of quinoline, but to a lesser extent. This was also shown by Satterfield. So the question we may ask today is the effect of nitrogen-containing compounds. One of the major problem in conversion is the conversion of basic compounds like alkyl anilines, which is difficult in the presence of other compounds as shown by Claude. And so I will report some results on the effect of 2,6-diethylaniline, which was used as a model of alkyl aniline on the HDN of quinoline. So as seen in the last paper of the morning session, quinoline is the model the most used to check the characteristic of the performances of catalytic system and also to check the influence of additives containing sulfur, oxygen, or nitrogen. So you find in this reaction scheme, you find all the elementary chemical states involved in hydrotreating reactions. So that is hydrogenation of the pyridine ring here, and this step and this one. Hydrogenation of benzenic ring here, 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 and here. You find also cleavage of carbon sp3 nitrogen bond here and here. And finally, the cleavage of carbon sp2 nitrogen bond. And this model is also interesting since results obtained under flow reactor conditions are similar to those obtained under batch reactor conditions, whatever the operating conditions under vapor phase or liquid phase. So I will remind you first the well-known effect of H2S on the mechanism of decomposition of dihydroquinoline and mainly the two chemical steps, hydrogenolysis of this CN bond and hydrogenation of this ring. So under flow reactor conditions, as shown by Satterfield, by increasing the amount of carbon sulfide, you observe an increase in the rate constant of hydrogenalysis reaction, and in parallel you observe a small decrease in the hydrogenation rate of tetrahydroquinoline. You can observe that the amount of orthopropylanilin also increases, as shown also by the partitioning coefficients between hydrogenolysis and hydrogenation. So one point to be noted here is that the rate of decomposition of tetrahydroquinoline remains nearly constant. So we have shown in our laboratory by adding directly H2S that the effects are similar. So an increase in the rate constant of hydrogenolysis, a decrease in the rate constant of hydrogenation, and an increase in the amount of orthopropylanilin 4. And one more time, the rate constant for the disappearance of tetrahydroquinoline remains nearly constant. So these two behaviors are illustrated on this graph from the data of Satterfield and from our own data. So we will see now the effect of 2,6-diethylaniline on the same reaction network. So we have performed two sets of experiments. First, using constant concentration in quinoline, and second, a constant concentration in nitrogen compounds. And as for H2S, you observe that by increasing the amount of 2,6-diethylaniline, the rate constant of hydrogenolysis of this CN bond increases, whereas the rate constant for hydrogenation decreases. So, and we can plot the amount of orthopropylanilin against the concentration of in diethylaniline, and you observe a similar behavior to that given for H2S. So by operating at a total nitrogen content, you observe also that by increasing the concentration in 2,6-diethylaniline and decreasing the corresponding concentration in quinoline, the rate constant for the hydrogenolysis step increases and the rate constant for hydrogenation decreases. And this is illustrated on this graph. And as for H2S, the sum of K1 plus K2 is nearly constant, whatever the operating conditions. So the question is how to account for this similar behavior between sulfur and nitrogen additives. Because it's well known that sulfided compounds and H2S in particular has acidic properties, whereas amines have basic properties. So we can imagine a kind of push-pull effect in which H2S will increase the number of hydrogenolysis sites as proposed by Satterfield, and we can propose that addition of amines will reduce the number of hydrogenation sites. So to account for leveling effect on the rate of disappearance of tetrahydroquinoline. So we have tried. So I report in this table the effect of diethylaniline alone and H2S alone, and the mixture of these two components. And we do not observe in K1 and K2 any significant variation, as well as in the rate of disappearance of tetrahydroquinoline, even here by K1 plus K2. So there is a kind of compensating effect between addition of acidic compound and basic compounds. So the influence of hydrogen sulfide on catalytic sites has been reviewed in literature. So first by Quark, Katzer, and Organ in '92, which suppose an equilibrium between anionic vacancies and branch-state acidic sites. So 1 year after, Satterfield proposed the same kind of equilibrium between anionic vacancies and the presence of hydrogen branch-state acid sites, but you can see that the role devoted to each site is different whatever, depending on the authors. So if we try to summarize these results, so the first idea is to consider this equilibrium like an acid-base equilibrium. So an equilibrium between hydrogenation and hydrogenalysis, so represented by these two steps, hydrogenation and hydrogenalysis, in which the addition of an acid component will increase the number of hydrogenalysis sites, so represented by sulfided additives. Neutral compounds like water, which can act as amphoteric substances, so are relatively without effect, whereas the addition of basic compounds will reduce the number of hydrogenation sites. And taking in mind that the resulting effect on the rate constant between hydrogenation and hydrogenolysis is nearly constant. So another explanation could arise from competitive adsorptions between nitrogen-containing compounds on these catalytic sites. So this can be seen by the results obtained by changing the ratio diethylaniline to quinoline. By increasing the amount of diethylaniline and decreasing the amount of quinoline, so we have observed that the hydrogenation rate constants are decreased, whereas hydrogenolysis are increased. So this is represented by the partitioning coefficients K1 and K2. And we will see, so in this work, we can see a moderate inhibition of hydrogenation of quinoline by 2,6-diethylaniline. And tomorrow I will present other results which will show a larger inhibiting effect of quinoline on hydrogenation of 2,6-diethylaniline. And I think that this was a question of this morning. So where we can ask the question, depending on the acidic properties or acid-base properties of the substrate, depending on the steric environment of the molecules and some other factors. So the problem can be posed in terms of accessibility of molecules to catalytic sites. So I'm sorry, that's all for today. Thank you very much.